Question 17. A violin is a musical instrument that has four strings as shown. A force extension graph for a sample of one of the strings is shown. You can see force on the y-axis and the extension on the x-axis. Always pay attention to the units of the axes. Force is in newtons, extension is in millimeters. The table shows the stiffness for samples of 3 of the strings on the violin. Each sample was the same original length as the sample used to obtain the graph. X string has a stiffness of 1700. String Y has a stiffness of 2700 newtons per meter. String Z has a stiffness of 6100 newtons per meter. Deduce which string was used to obtain force extension graph. For this, we will have to determine the stiffness of the string which is represented by the graph. As I have explained in a previous question, in a force extension graph, gradient represent the stiffness. So gradient equals to stiffness. Therefore, we have to identify the gradient of this graph. So we can see it's easier to get 2 points on the straight line. It's better if the 2 points are furthest as possible. So I would consider the origin, which is 0, 0. We have one coordinate, and the other point is the end of the straight line. Approximately, the force or the y coordinate here is 80 newtons, and the x coordinate is 29 millimeters. Now we can calculate the gradient. Gradient is difference in y coordinates divided by difference in x coordinates. So the difference in y coordinates are 80 minus 0. I'm not going to write the 0. Difference in x coordinates is 29 minus 0. Again, I'm not going to write 0. However, the extension is given in millimeters. Therefore, we have to convert this into meters. Multiply 29 with a factor of 10 to the power minus 3 to convert into meters. This would give us the stiffness of the material. The calculation gives us an approximate value of 2760 Newton per meter. Now, if we compare this value with the values given in the table, we can see the approximate answer is approximate stiffness is for string Y. So the sample that is being used must be sample Y. For this question, you get 4 marks. 1 mark is for the calculation or reading the data from the graph and then calculation. Using f equals kx, 1 mark, and the final value of k gives you 1 mark, and the last mark is for a statement writing the comparison between the table and the values you obtained. Let's move on to part B of the same question. The fourth string on the violin has an original length of 0.750 meters. When the tension applied to the string is 36 newtons, the new length of the string is 0.752 meters. The radius of the string is 0.85 times 10 to the power minus 3 meters. Determine the Young's modulus of the material used to make the string. We know that Young's modulus can be calculated using the ratio of stress applied to the material and strain of the material. So stress applied to the material can be calculated using the force over cross-sectional area. Let's first calculate the stress applied to the material. So the force is 36 newtons and divided by cross-sectional area. Okay, so we don't know they have not given us the cross-sectional area directly, but they have given us the radius. So we can calculate the cross-sectional area using pi r squared. Since it's a string and the cross-section of a string is circular. So we can use pi r squared. Therefore, it gives us pi times 0.85 times 10 to the power minus 3, everything squared. This calculation would lead to approximately a value of 15.9 times 10 to the power 6 pascals. The next quantity we need to calculate the Young's modulus is strain of the material. Strain is defined as the ratio between extension and the original length. In this problem, they have given us the original length to be 0.750 meters. However, the extension is not given directly, but they have given it as new length and the original length. So we know that extension can be found by the difference of the new length and the original length. So if I get the difference between 0.752 meters and 0.750 meters, the extension would be 0.002 meters. This calculation would lead to a value of 0.00267. Now we have obtained stress and strain values, and the Young's modulus can be calculated using the division of these two values. That would be 5.96 times 10 to the power 9 pascals. So we know that Young's modulus is given in pascals. Here you get 5 marks for this problem. 1 mark for the calculating cross-sectional area, 1 mark for calculating stress, 1 mark for calculating strain, 1 mark for showing the steps of determining Young's modulus, writing stress over strain. You can use symbols, standard symbols, and then final mark is for the final answer.